Okay, I'm going to illustrate the use of a power rule for computing derivatives using several examples. So here I have 6 functions, and I'm going to show you how to apply the power rule to each one. So for this first one, the function y equals minus 7x plus 5, it's a sum of 2 terms. Now when you're computing a derivative of a function that has more than one term, you can take the derivative of each term individually and then add up the results. So I can take the derivative of minus 7x and then a derivative of 5 and add those two together. So y prime is, so to illustrate what I just said, it's a derivative of minus 7x plus the derivative of 5. Now, the next thing we can do to break things down is when a function is multiplied by a constant, the derivative is its derivative is multiplied by that same constant. So I would have minus 7 times the derivative of x plus the derivative of 5. Now, the power rule, I'll write over here that the derivative of x to the n is n, so the exponent n comes down here, times x to the n minus 1. So pull the exponent down and then subtract 1 from the exponent, and there's your derivative. Now here we just have x, but x is the same as x to the first. And then 5 is a constant. You can think of it, if you want, as 5 times x to the 0, because x to the 0 is equal to 1. So I can write it that way. Now, I don't expect you to write it like this when you're working these things out. I'm just explaining where the answers come from. So, applying the power rule, we have minus 7, and then the derivative of x to the first is 1 times x to the 1 minus 1. And then, if we apply the power rule to x to the 0, which is 1, you pull that exponent down and you're going to get 0, so the derivative is going to be 0. So derivative of 1, which is the same as x to the 0, is equal to 0, which makes sense because what is a derivative? It is an instantaneous rate of change of a function. And a constant function is not changing at all, so its rate of change would be 0. Now to simplify what's going on here, we have minus 7, and then x to the 1 minus 1 as x to the 0, which is 1. So we're left with minus 7. So it turned out that the derivative of a function like this that describes a line is the slope. And that's true of linear functions in general, and it's something that's good to remember. So the derivative of 1 is 0. And if we multiply that by any constant, so the derivative of any constant function is 0. The derivative of x, as we see here, turns out to be 1. So these are good things to know, but you're not going to actually go through the whole process of carrying out the power rule. You can just remember these. Now, for a second example, we have 2x to the 4th. So the derivative of f of x is written this way, f prime of x. So that would be 2x to the 4th prime. Now, when it's multiplied by a constant, we can pull out the constant and then take a derivative of x to the 4th. So since x to the 4th is multiplied by 2, its derivative will also be multiplied by 2. So now we use a power rule. So we bring the exponent down, and we have x, and then we subtract 1 from the exponent, and we get But the derivative of x to the fourth is 4x cubed. But don't forget, multiply everything by 2. So our final answer is 8x cubed. So that's the answer for our second example. And just as minus 7 is the final answer to our first example. So one thing I want to point out before I move on is notice that when a constant is added to a function, it makes no contribution whatsoever to the derivative because the derivative of a constant function is 0. On the other hand, like I said a couple of times already, if a function like x to the fourth is multiplied by a constant, for instance it's multiplied by 2 here, the derivative is multiplied by that same constant. So a constant factor, something that's a constant that's multiplying the function, that sticks around. A constant that is added to a function goes away. So it's very important to keep that distinction in mind. Okay. For our third example, minus 2 over x squared. Before I use the power rule, what I need to do is write this function in a way that, in such a way that it fits the form of the power rule. I'm going to give myself a little more room here. So minus 2 over x squared. I'm going to rewrite that as minus 2x to the minus 2 power. Okay. Now, as before, dealing with constant factors, this is called the constant multiple rule. F prime of x is going to be minus 2 times the derivative of x to the minus 2. So we can just focus on taking the derivative of x to the minus 2 and then multiply the final result by minus 2. This factor is sitting out here. So, when we use the power rule, it works the same way for negative powers as it does for positive powers. We bring the exponent down, and then we subtract 1 from the exponent. So we get minus 2, x to the minus 3. And then we combine everything, and we get minus 2 times minus 2 is positive 4, x to the minus 3. So we could stop there. That is the acceptable final answer. But I can also write it in this form, 4 over x cubed. So we see how we handle negative exponents. We rewrite the function in a form so that it fits the power rule. The power rule is applied to x to the n, not a power of x in the denominator. Now, here we have an example of a different sort, 2 times the square root of x. So we need to rewrite that function as well. So we can write it as 2x to the 1/2. So remember, the square root of x is the same as x to the 1/2. The cube root of x is x to the 1/3, and so on. So once we get in this form, now we can use the power rule. So y prime is 2 times the derivative of x to the 1/2. So the 2 is a constant factor, it just stays there. So now for applying the power rule to x to the 1/2. Okay, so for applying the power rule to x to the 1/2, we have the exponent coming down, 1/2, times x to the exponent minus 1. So we have 1/2 minus 1. Now, to simplify this, you have to be careful working with fractions. We have 1/2 minus 1. We should put everything over the same denominator, common denominator. Well, 1 is 2 over 2. Now, both fractions have the same denominator, so I can combine them and have 1 minus 2 over 2. So that's minus 1/2. So that is going to be our exponent up in here. So we have 2 times 1/2 x to the minus 1/2, which can be simplified because the 2 and the 1/2 will cancel. So now we have x to the minus 1/2. Now, that can be rewritten as 1 over x to the 1/2, because a negative exponent in the numerator corresponds to a positive exponent in the denominator. And then this could be written as 1 over the square root of x. So that is our final answer for this example. So when you have a function under radical sign, what you need to do before using a power rule is rewrite that in terms of the appropriate fractional power. So, for instance, I'll do another example. Suppose we have the 5th root of x to the 4th. So that would be rewritten as the power of x goes in the numerator. Whatever root you're taking goes in the denominator. So this would be the same as x to the 4/5. Okay, now returning to our sample functions. We have minus 4x to the 9.2. So now the exponent is expressed as a decimal. But the power rule works in the same way. So f prime of x is going to be equal to the constant factor out front, minus 4, times the derivative of x to the 9.2. So applying the power rule, the 9.2 comes down, and then we have x to the exponent minus 1, so that would be 8.2. And then we can simplify by multiplying the minus 4 and 9.2 together. That would be the same as taking the 9.2, doubling it twice, to multiply by 2, then 2, and then negating it. So we'd have 9.2, we double that twice, we get 18.4, and then 36.8. So we have minus 36.8 x to the 8.2. So that is our final answer for that one. And finally, we have another example of a fractional exponent. G of x equals x to the 5/6. So this exponent is already in the proper form for using a power rule, because this could also be written as the 6th root of x to the 5th, but that doesn't help us with computing a derivative. So g prime of x is equal to, so the exponent comes down, 5/6, and then we have x to the 5/6 minus 1. We're subtracting 1 from the exponent as always. And again, put everything over a common denominator. So that would be 5/6 x to the 5/6 minus 1, which is the same as 6 over 6. And now you can just subtract the numerators. So we have 5/6 x to the minus 1/6. And there you have it. So here we've seen how the power rule can be used for a variety of situations with different kinds of exponents, negative exponents, fractional exponents, exponents expressed as decimal. But no matter what kind of exponent it is, a power rule always works in the same way. And don't forget, when they're implied exponents, the derivative of any constant function is 0. The derivative of just x by itself is equal to 1. So it's important to keep those shortcuts in mind.